measure from where it starts out. Essentially, this is the range to where it lands. So someone has to, basically we need to have a shooter. The shooter orients this at just the right angle. You take your protractor, lay your protractor flat on the ground, set up your gun to where maybe you need this to be 30 degrees. We're going to vary this angle. You set your gun up to where it's right, sitting right on the ground. In order to do this, you're going to have to lay flat on the ground. I don't think there's any other way, unless you have a really, really, really long table. You lay this flat on the ground, set the angle, shoot it, then you have a spotter over here who spots where this lands, and then you measure the range. The range will be from where you shoot to where this lands. Okay? And if you look at how this is set up on page 4, of course the range equation is this. That's the range equation that we're going to be using. But we're going to vary this from 5 degrees to 15 degrees to 25 by 10 all the way up to 85 degrees. So we're going to be varying this, and we're going to be doing 3 repetitions for each angle. So for 15 degrees, we'll do 3 repetitions, etc., etc. The table is the way the table is laid out. You have the angle, you calculate the sine of twice that angle, and then you calculate, or excuse me, then you measure your ranges. You take the average, and then on part 5 is where you have your analysis. And simply go through the analysis. What you're going to be doing is on page 6, you're going to be making a graph, and the graph needs, it's a 2 charts, and the 2 charts need to be something, look very similar to what's on page 5 is an example. The first part of the graph, well, excuse me, in the first graph, and this is explained on page 5, but in the first graph, you're simply going to make a plot of the angle from like 5 degrees on up to 85 degrees, and this is the range. And this should look something like, it should go up and then it should come down, and it should look something like that. Draw a nice smooth curve through that. In the second graph, right below it, on the same graph paper, what I want you to do down here is to plot the horizontal distance, or horizontal axis, is sine of 2 theta. Okay, sine of 2 theta. So what that means is you'll take your, for instance, for 5, if this were 15 degrees, you would take the sine of 2 times 15 degrees. Well, 2 times 15 is 30. Take the sine of 30 and you would plot that. And then over here you would plot the range, x range. Now why are we doing this? I'm going to erase the top chart. If we take the range equation, is VO squared over sine of 2 theta all over G. We're going to plot this equals something times sine of 2 theta. Okay, so it's the x range times this. So notice this now, the slope simply becomes VO squared over G. assuming the initial velocity is constant, which it will be, what this should be, this should plot up as a straight line. If we plot x range versus sine of 2 theta, we should get a constant slope here, where this slope is VO squared over G. And this is a way for us to actually, assume we know what G is, the acceleration of gravity, so we can back calculate what the initial velocity was from measuring the slope. That makes sense, I hope? Okay. And then there are some questions on page 7 dealing with all of this. Okay, in part C is where we're hoping we get somebody with a potato launcher or a balloon launcher, and we're going to take some data out in the field with one of a potato launcher or a balloon launcher, weather permitting, and if somebody has one of these devices. And so that will be part C. Now, there is an extra credit problem. The extra credit problem actually comes out of a comic strip. Yeah, kind of funny. If you read the comic strip, it talks about a physics equation. The question is, you read the comic strip, you'll get a good laugh out of it. Then the question is the equation, the physics equation that's in the comic strip, is it true or not? Is it just a fictitious equation, or is it a really true equation? To really know for sure, you're going to have to do some derivations. It's a little bit tricky. All of you are capable of doing it, but it's a little bit above and beyond, and that's why I'm giving it an extra credit problem. Okay. That's the first lab. The second lab is a numerical lab. And this is a lab where you're simply going to calculate you're going to calculate a projectile motion, but you're going to calculate it using Excel or some kind of spreadsheet. If you don't have Excel and or some kind of computer spreadsheet, you can certainly calculate this by hand, but it's a lot of calculation. So I want this to really be an exercise for using Excel, but using Excel or some spreadsheet for calculating projectile motions for physics. On page 1, part A, what I do is I show you the derivation, I show you the equation of a equation of y is f of x. I will write the equation here. Y is minus g over 2 the initial velocity squared times cosine squared of theta. All of that times x squared plus tangent of the angle times x. Okay. Now, part A is to derive this equation. Okay. It looks a little tricky, but there is a little bit of a trick to it, but all of you should be able to derive this equation from all the two-dimensional physics equations that you have in Chapter 4. Okay? This is not derived in Chapter 4. However, you should be able to take the equations. Basically, what basically is this? What this is this. If we start at the origin, this is x, and this is y, and we shoot an initial projectile at a certain angle with a certain velocity, we know that this is a projectile motion. The actual shape of this curve is y equals f of x, and that's what this is. This curve, this is a parabolic curve, and the shape of this curve, the equation of this curve is given right here. Now I've derived it, and I want you to derive it for part A. If you have any questions, if you have any problems and you want to get a little initial head start on this, or you can't figure out how to get started, go ahead and call me or send me an email. But I want you to think about this, struggle with it a little bit. The physics is learned in the struggle of trying to solve the problem. Don't forget that. If you have initial problems with trying to figure this out, that's good. That means it takes work, and it's good to think about things, and it's good to solve these problems. That's where mastery over the physics and mathematics comes from. In part B, what you're going to do is you're going to take this equation, and what I want you to do is to put it into an Excel spreadsheet, very similar to what I have on page 2. I've laid out a table here. You can calculate this by hand, but I really would rather you calculate all of this in Excel. It would be much quicker, for sure. Once you calculate it, I then want you to plot it. Now, you don't have to plot it here by hand. I'd rather you plot it right in Excel. And what I want your plot to look like is, well, I want it to look just like this, where you have x and y, and you plot it at different angles. Like this may be the angle for, let's say, 35 degrees. Then you plot another one for 45 degrees, and it may do something like that. Okay? And then plot one at 55 degrees. And so I want you to have several plots. In fact, I want you to have all the plots all on the same graph. Okay? And that really is the slab. There is a starter kit, a starter Excel file that I will send you to help you get going, but you don't have to use it. So if you have any questions on any of this, feel free to call me or send me an email. Well, good luck on all this, and I know you can do it. Bye.